University. So it is the last lecture of our short-time course. So Professor, good morning.
Good morning. Good morning.
Yeah. So how are you?
Good, not too bad. Things are okay here still.
Okay. So had a breakfast?
Yeah. Those things are finished. Long
Yeah,
time.
we
It's
are going
already
to have a lunch.
10:30 here, so that's good. It's about, yeah.
Welcome, Dr. Abhishek. Welcome.
Thank you.
Yeah.
Thank you very much. Thank you. So I'll try sharing the slide now, and hopefully things will be. So can you see the slide?
Yes, sir. Can you move the next slide? Yes, perfect, sir. Working perfect. Yes.
Okay, good.
Yeah.
Good afternoon, everybody. This is the final lecture for this short-term course. I hope many of you have learned a lot from this course, or you have got enough takeaway home message for you to pursue further research, as well as get an overview of various topics of material synthesis and quantum dots for various applications. Here in today's final lecture, in the next 1 hour, what I intend to give you is the topic on nanomaterials application in solar cells and sensors. I guess Dr. Ravi already gave you a beautiful talk. I have heard only the end of that, and it was pretty beautiful in understanding perovskite-based solar cells and how perovskite-based solar cells have been developed. Yesterday, I hope Mani gave you the good talk on two-dimensional structures of in how you can build sensors based on this. So my talk over here won't be able to, it'll just complement the two lectures. It won't substitute the brilliant lectures both the lecturers have given. What I intend to do in the final lecture, everybody has taken a specific topic, and as I've been presenting on different nanomaterial synthesis, I will keep the lecture as an overview of the methods of the different solar cells and sensors, and then give you, once you have the overview, then you will understand where the challenges remain. Once you understand the basic principles of how things are working in both the case of solar cells as well as in case of sensors. So with that, let's continue with the final lecture. So I'll start with solar cells, and then I will take you through sensors. Now, I guess everybody is quite aware that there are various types of solar cells available in market. We have the monocrystalline solar cell, which has been there for at least 20-30 years now, and it has the sort of the highest efficiency as per what the record is. It's the efficiency rate is between 20 and 25%. And it has a very wide lifespan of about 25 years. These are based on monocrystalline silicon, and therefore developing these monocrystalline silicon is a costly affair, and therefore these solar cells are very expensive. So unfortunately, there is, as yet, there is no sort of substitute for these monocrystalline silicon based on their efficiency as well as their lifespan. We will look into these aspects as we go ahead. Then you have the polycrystalline solar cells. Again, these are silicon based, and the efficiency rate is between 16 and 20%. Again, they have a very wide lifespan of about 25 years. They are less expensive compared to the monocrystalline, and also they have lower cost compared to the monocrystalline solar cells. And finally, we have the thin film solar cells, which have a wide variety of efficiency. It can go from all the 5% all the way to 25-30%. However, the lifespan is quite low. It depends on the lifespan of the various solar cells. It can last between 5 and 15 to 20 years. However, there are still improvements needed in different kinds of thin film solar cells. But these solar cells are much less expensive and rather easy to produce compared to the silicon solar cells, which needs a controlled atmosphere and controlled environment conditions. However, these compared to these silicon-based solar cells, there's still challenge in improving the efficiency of these solar cells. So let's look at the solar cell efficiency. Now here we have a graph which shows the efficiency in y-axis with the year, and we can see that from 92 to 2014, this is the year range which we are looking into. One can clearly see from this the monocrystalline and polycrystalline, which is marked as black lines over here and the red lines. The efficiency has basically is almost stable. There's no change in efficiency. Obviously, you cannot change the efficiency of these solar cells. Even if you dope it, you're going to reduce the efficiency. You won't be able to improve the efficiency. And as well, when you have a monocrystalline structure, that means you don't have defects. You have defects, although you have defects, but they are very, very small defects. And to remove, to make it defect free, well, thermodynamics third law says that you cannot get it if you don't go to 0 degree Kelvin. So that's where we are stuck with. We cannot have a defect free structure. So therefore, monocrystalline and polycrystalline silicon has been a constant, having an efficiency about 20 to 25%. So 20% in case of polycrystalline and 25% in case of monocrystalline. Now there are various other solar cells. Now what you see in the yellow curve over here is a multi-junction solar cell. So you have tandem-based solar cells combining various things, and they have a very high efficiency. It's gone up to above 40% in the last couple of years. However, there are other issues which we will discuss in a couple of slides later. And you have various other organic solar cells which were developed into 2007, and then they started to improve. They have an efficiency of about 15%. But again, there is always a contradiction between the efficiency and the lifespan, stability issues. So these are some of the issues in the case of solar cells. So if we look into the classification in terms of highest efficiency, we still have the monocrystalline and polycrystalline way ahead. So the efficiency is between 20 and 25%, and the fill factor, which is nothing but a combination of the open circuit voltage and the short circuit current. The short circuit current is JSC and open circuit voltage is VOC. You have already seen that in the last lecture. So within a vast area of 143 centimeters square, if you take that amount of area, you have a relatively high fill factor of 82.7, and with a large wide lifespan of 20 to 25 years, which doesn't degrade much. Therefore, these solar cells are still prevalent or compared to any other kind of solar cells. I think many of you would have heard, must have heard about multi-junction solar cells, which are moving upwards and will possibly compete in the next 5 to 10 years with the monocrystalline and polycrystalline solar cells, because they are much easier to make. These solar cells are still a challenge. So for example, if we take the Dyesensitized solar cell, it gives an efficiency of 12%, and I guess from EPFL, the recent result was about 15 to 16%. They have improved the efficiency based on the die. Perovskite solar cells are the new generation solar cells, which was developed in 2004 to 2008, and it has shot up into the market, where the efficiency has gone all the way above 22-23% at present. So we'll look into the DSSC solar cells and perovskite solar cells a bit more from the next slide. So let's look at what the dye-sensitized solar cell is. So this is the schematic diagram of the usual dye-sensitized solar cell. You have a transparent conducting glass such as ITO or FTO. So you have indium tin oxide glass, it is a transparent glass. You have the metal oxide, it can be titanium dioxide, zinc oxide, it can be doped materials. And then you have a dye which is on this metal oxide. So dye, the usual dye in dye-sensitized solar cell is N3 or N719. These are basically organic dyes. So the metal oxide and the dye is in contact with a redox electrolyte where you have a electrochemical reaction taking place, and then you have the counter electrode, which is a layer of platinum or gold. So it acts as a catalytic layer, and then you sandwich it between the two conducting glass. So what really happens in the case of dye-sensitized solar cell? So the schematic diagram shows what is really happening in dye-sensitized solar cell. So it's the same thing which is happening even in perovskite solar cells. So when the sun shines on these kinds of solar cells, the dye absorbs the energy, and once the dye absorbs the energy, because it absorbs the energy, the electron can go from the HOMO layer of the dye to the LUMO layer of the dye. Once you have a jump in energy, then there is a transfer of energy from the dye to the metal oxide. So this is where the electron is transferred. So the HOMO and LUMO level of the dye has to match to the conduction band of the metal oxide. Once there is a match between the HOMO and LUMO with the conduction band of the metal oxide, then you can easily transfer, or the electron is automatically transferred to the band of the metal oxide. And then you go through the outer circuit. So it goes through ITO. You use this solar cell for charging or storing the charge. And then it goes to the other side. It enters the platinum. At the platinum, the electron basically goes through a electrochemical reaction in the electrolyte. So you have a reduction of I minus to I3 minus. And what happens during this electron, the electron goes back to the dye, and you're regenerating the dye. So you have lost the electron over during the charging case where the sunshine is shining, and then you regenerate the dye so that it goes back to its original state. So this is the whole process of how the dye-sensitized solar cell works, as well as the perovskite solar cell works. So now one can clearly see that the interface between the metal oxide and dye becomes an important aspect in order to have a proper or an efficient way of electron transfer from the dye to the metal oxide. Now, if you don't have this interface, which is between the dye and the conduction band or the metal oxide, to be very good, then you're going to have recombination reactions. What are recombination reaction? You have the electron and the hole. At some point, you're going to generate electron and hole, which then combines together, and therefore you won't be able to separate out the electron and hole from the dye to the conduction band. And usually recombination reaction takes place at the rate of 10 power minus 11 seconds. So that's the rate at which you will have to separate the two electrons. So therefore, a lot of theoretical work is going on you can do this simulation using density functional theory, where you're going to match the metal oxide with the dye and see whether there is a charge transfer which can take place. There is a overlap between the conduction band of the metal oxide and the HOMO-LUMO of the dye. So there are lots of research going on, especially in creating better dyes which can easily help in this charge transfer to take place, and as well as to match the band gap between the conduction band of the metal oxide and the HOMO-LUMO of the dye. Also, again, this is the one interface which is taking place. You have the second interface between the electrolyte and the dye, which also is very important. So the electron has to transfer from the electrolyte to the HOMO level of the dye. So that is equally important. So one has to match both the properties of the dye transferring electrons and getting electrons from the electrolyte. So both the process is equally important. So with that, as we have seen what the dye-sensitized solar cell can do, let us look at some of the examples of the photoanode. That because we have gone through all the material synthesis, let's look at how these different material synthesis has affected the performance of the solar cell or dye-sensitized solar cell. Now the photoanodes which we will choose are the three traditional photoanodes for dye-sensitized solar cell. They are titanium dioxide, zinc oxide, and niobium pentoxide. Now all the three oxides are very relevant for dye-sensitized solar cell. They have been extensively studied, so I'm just going to summarize these results. Now what is interesting is that when you produce different morphology or different structure of these three materials, they sort of affect the performance of the dye-sensitized solar cell. Now all the three materials, the different techniques were used, such as solvothermal, hydrothermal, electrochemical anodization, and electrospinning techniques were used to synthesize these materials. So you produce nanoparticles, nanorods, nanochannels, and nanofibers. And then many research groups compared how the various morphology affects the dye-sensitized solar cell. So we will take these three examples and see how different morphology is affecting the performance of dye-sensitized solar cell. So here we have titanium dioxide photoanode. You have various structures. You have the nanoparticles over here. You have nanowires. You have the porous structure, anodized porous structure. You have nanorods and various other porous structure. So let's see how the various structure basically affects the dye-sensitized solar cell performance. So this table basically summarizes the various morphology. So they have different titanium dioxide morphology. And here you have efficiency, fill factor, open circuit voltage, and short circuit current. And the electrolyte is liquid electrolyte, which is the iodine redox reaction. The dye is slightly different for different material. But overall, the dye has the matching dye matches the energy bands of the dye matches with the dye of with the conduction bands of titanium dioxide. So here one can clearly see from this table that the highest efficiency between 10 to 13% is achievable for when you have titanium dioxide nanoparticles and when you use N3 or SM315 dye. We have a reasonably high fill factor, which is about 74% or to 78%. For the case, just for the reference, the fill factor in case of silicon is about 85%. So we are very close to what the fill factor in case of the silicon is, the traditional solar cell is. However, the efficiency is relatively low. However, if we compare the nanoparticles with various other structures such as nanotube, nanorod, nanowires, or microflowers, one can clearly see that none of them have reached the 10 to 13%. They have all gone downwards. So what is the reason behind having nanoparticles as a better material for dye-sensitized solar cell compared to any other structure? Although one can always argue that in case of nanotubes, we are having much higher surface area. You have an inner surface area and outer surface area. So we have a very high surface area. However, when we make these solar cells are usually developed by spin coating the material. And dispersion of nanoparticles is much easier compared to dispersion of various other materials. And it is not always the surface area which influences the performance. Because in case of nanorods, there is no point having, in case of nanotube, there is no point having the inner surface area. Here we are in these nanotubes basically will help in recombination reactions rather than splitting the electron and hole system. So therefore, one has to think beyond when you develop a material and test it. One has to pre-think which material would give you sort of the best result and why it would give you the sort of best result. So critical thinking before performing the experiment is an important aspect, which is usually done very critically. And if you do critical thinking before running or developing an experiment you will often see that your results are more efficient. So with less number of experiments, you will be producing more results. Let's move on to the next material, which is zinc oxide photoanodes. Again, we compare the three materials. We have nano tubes, we have nanoparticles, we have nanorods, and you have various other nanoflowered structure. So if we look into the performance of dye-sensitized solar cell, again, it's nothing, it's quite obvious. We have zinc oxide nanoparticles, which has the highest efficiency of 6.58, having a fill factor of about 58-59%. Whereas if you have various other structures, then obviously the efficiency drops down. So one can clearly see again that it's not always the efficiency of the dye-sensitized solar cell depends on the morphology. Again, it depends on the morphology and not always the surface area. Finally, we go to our third example, which is on niobium oxide. Here again, we will compare the three things. We will compare the nanotubes, nanowires, and various other nanostructures. And one can again see, okay, here we don't have the niobium nanoparticles, but in this case, the nanorods have the highest efficiency compared to nanopores or different other nanostructures. Now, if we compare all the three oxides, niobium oxide, zinc oxide, and titanium dioxide, one can clearly see that titanium dioxide gave the highest result because there was a good transfer of, or the recombination process was quite less in case of titanium dioxide compared to other oxides. So here one can, how do you improve your dye-sensitized solar cell? The only way you can improve it is by improving the charge transfer process between organic dye and the titanium dioxide nanoparticles. One has to look into the recombination process, where how would you improve the recombination process? So one way is to reduce the defects in your material and to improve the charge transfer process between the organic dye and the metal oxide. One has to develop new kinds of organic dye. Again, in that place, the interface between the dye and the metal oxide and the dye and the electrolyte plays a very important role. So both theoretical and experimental theoretical calculations along with experiment would give you a better, that's the way to go forward in order to improve the performance of dye-sensitized solar cell. So now let's move to the various factors which affect the performance. One, we have clearly seen that the synthesis method or the morphology affected our performance. The surface area was another factor which influenced the performance. Charge transfer characteristics such as the electronic conductivity is also an important aspect because titanium dioxide and metal oxides are not very good electronic conductor. They are not good electronic conductor. So therefore, how would you improve the conductivity of these electrons? And if you have defects in titanium dioxide, then obviously you're again having a recombination reaction which can take place within the metal oxide system itself, and therefore that is an issue which one has to look into. And finally, the electron hole combination based on the dye and the metal oxide. So now let's look into the next aspect of solar cell, which is an emerging topic. I think Professor Ravi basically gave a lot of input into various perovskite solar cells and showed how the aluminum doped tin oxide gave a wonderful result. There are still a lot of challenges which are is a problem in perovskite solar cells, and we'll look into what the challenges are in case of perovskite solar cells. Now, perovskite solar cells basically started way back around 2002-2003. Perovskite is a very well-known structure, especially if somebody is from mineralogy, they will know perovskite structure straight away. It is a very, very stable structure, and it has been known for over 150 years about perovskite structure. So perovskite solar cell, so therefore because of its stability, nobody really thought perovskite could be used in case of solar cells for generating electrons. However, in 2003, they first showed that there was possibility, 2008, there was some possibility of perovskite being used as solar cell. And because of piezoelectric research which has been done over the last 50 years, it is well-known process of how to develop these perovskite structure. So in 2008, the first perovskite solar cells were shown, which had an efficiency of about 3.8%, and within 2014, the efficiency was rapidly improved to 15.9%, and now the latest perovskite solar cells have shown an efficiency of about 24 to 25%, which is competing with silicon-based solar cells. And why is this research happening so rapidly? Because people know how to make perovskite solar cells. It's a well-known technology. So before we go into the problems of perovskite solar cells, I just wanted to let you know what perovskite is. What is perovskite? So perovskite is basically any material having a stoichiometry of AMX3 or ABX3, whichever you prefer, where A is the cation, such as calcium, potassium, sodium, strontium, any rare earth metal, transition metals, any cation. M is the metal cation which sort of coordinates with 6 oxygen atoms or 6 halide atoms. So basically what you find in the crystal structure of perovskite is this MX6 octahedra structure. So you have this ABX3. So some of the very stable perovskite structure is calcium titanate. And if you have gone to Kerala beach, if anybody has gone or visited Kerala beach, the material which is on the beach is called ilmenite, which is FeTiO3. So this is another basically perovskite structure where the TiO6 octahedra is present in the crystal structure, and it is basically a stacked structure with iron at the interstitial sites. Again, in calcium titanate, you have exactly the same thing. TiO6 forms the octahedra, and you have in between it is stacked with calcium atoms. So basically, you can see that because it's a beach sand, it is going to be very, very stable. And therefore, perovskite-based crystal structures are very, very stable structure, and usually does not undergo corrosion, especially the ones which are available in the mineral phase. However, we are trying to synthesize perovskite structure in our labs, and therefore things become much more difficult especially when you're making these when you're adding transition metals into the perovskite structure to reduce its defect and other properties. Now, the ones of the perovskite which is basically used in solar cells are based on organic, inorganic materials which have shown very high efficiency. And once you make perovskite using organic and inorganic materials, then obviously the stability of the material and defect stability of the material sort of decreases. Therefore, the present challenges in perovskite solar cells are the degradation time, effect of humidity and temperature, its stability, and for perovskite to become a player in the power market. So if you look into if it has to compete with silicon-based solar cells as well as dye-sensitized based solar cells, it needs to have a stability or lifespan of about 20 years with minimum degradation. So these are some of the challenges. So at present, the perovskite solar cells do not degrade pretty quickly, because I said that it is, if you want a high efficiency, you have to go towards an organic, inorganic material based perovskite structure. So these are some of the challenges. It's an upcoming topic, an emerging topic of great importance, and I hope in the next 5 to 10 years there will be a tremendous improvement in the conversion efficiency as well as improving the stability of these perovskite solar cells. So now that I've just given you a brief outlook of what the challenges are and how the solar cell overall background of solar cells, for you to sort of think in how you can develop new materials using the various techniques which we have already seen during this short course, in order to improve the case or improve these solar cell structures. So now we will go into the next topic, which is of sensors. And I guess yesterday you already have looked into various sensors, in case of where Mani has already shown you various sensor application. Now I'll give you again an overview of the different types of sensors which are available. Now, in case of sensors has vast application. For example, here in the room we have a fire sensor. So if there is smoke, we have a smoke detector. Smoke detectors are nothing but sensors. There can be biological biosensors, which are absolutely vital, especially in the COVID times. One can think of developing very quick sensors for COVID detection. You have various gas sensors, and in case of if we go more into biosensors, one can look into how whether when one takes medication, how one can look into whether the medication is working or not. You can make a sensor out of it for understanding how the body fluids are working, how the antibody is working, or how the peptides are working. So there are lots of opening or lots of research being done in case of biosensors, and biosensors have various applications.